to Whanganui, and it's a great pleasure to be back here again. It seems just yesterday I was here on that hot February night talking about earthquakes. So today I thought I'd focus not only on earthquakes, because they are of course very timely, but also a little bit on, go beyond that and also look at the hazards that this area of Western North Island, Whanganui in particular, might be subjected to from volcanism and sea level change. And sea level change is a particular aspect which has become much more relevant in the last few years. Yeah, it was very interesting having this earthquake this afternoon because it occurred right beneath this line of earthquakes here between which occur between Mount Ruapehu and Mount Taranaki. We call this the Taranaki-Ruapehu, but at 200 kilometres deep. So it's a very interesting earthquake. And fortunately, one of my graduate students he instantly analysed, did some analysis, and sent me a couple of pictures, which I'll show you with some of the results that have already come out on that. But let's start with earthquakes, because in terms of costs to New Zealand, this is really the only game in town at present. If we look at the data, this is from the Natural Hazards platform, and it's in billions of dollars since 1843. The equivalent dollar term today, earthquakes by far cost us the most amount, about $80 billion. Tsunamis, volcanic eruptions and floods. So this is in today's dollars in terms of what it's costing us. So it works out since 1843, if you add all those up, it's about $500 million a year. And so that is a real cost for a small country like New Zealand. But the other aspect, which has just become, this came out in the paper just last week, is the way we're perceived by insurance companies. And this is really important because this hits us in the back pocket. And we're seeing now as a very high risk, and this is largely because of the recent earthquakes, and we're the second ranked in the world, and it's not really where we want to be. But this is really largely because we have a very small GDP, because we're a small population. But this is the other side of hazards, which is becoming more and more important for us, because this is how you'll see it on your insurance bill. I don't know about you, but my house insurance has doubled since the Kaikoura earthquake. I'm not quite sure how it is in Whanganui, but the insurance companies take a very dim view of the Wellington area. So it's important to then understand how different parts of New Zealand may be affected by earthquakes and sea level rise. And that's really what I want to talk to you today about, is see where we sit, where the Western North Island and Whanganui features in this sort of hazard scenario. And in fact, it's not all, you're by far better off than most parts of New Zealand, as I'll come to show. So when it comes to earthquakes, can we predict earthquakes? And this has often been asked by many people, and some people suggest that we can, but to do this you need to make there's three factors you must have right: the location, the magnitude, and the time. And more often than not we can get two. It's very easy to pick any two combinations, but getting all three right is almost impossible. In fact, most people now regard it as impossible. For a period in the 1970s, there was quite a lot of excitement that the various phenomenon that could be used to predict earthquakes, but it never came to fruition. And so if you go to the US Geological Survey, who are authorities in this area, and ask this question, can scientists predict earthquakes? It's quite emphatic, no. And it's unlikely that we'll ever be able to predict them. But what we can do is forecast, just like weather forecasting. We can suggest areas which are likely to have them and even put a probability to it. And to do this, we need to take a sort of physics-type approach and try and learn about what's happening beneath the ground surface and understand how we can interpret different parts of the world, and even different parts within New Zealand, different parts of New Zealand, and look at the risk. I think I showed this last time. This figure really gets across this idea that the trouble with earthquakes, trying to predict earthquakes, these are magnitude of earthquakes from 7.8, these are very large ones, up to 9.6 since 1900. And you can see there is, it looks a bit of a scatter, but you can see there's a sort of peak around 1960s, the big Chile earthquake, and then it was very quiet up until about, just recently, about 2005 or so, we started with the Sumatra earthquake, and then the big one in Japan. And so if you were going to be a statistician, you might put a line through that and say there's a cycle going on here. But we've only got one cycle. This is since 1900, where we had instruments which could measure magnitudes of earthquakes properly. So this is our problem. Compared to weather forecasting, which has also been gone since about 1900, they get a cycle every day, every week. They've had hundreds and thousands of cycles, literally, to make their predictions on. Whereas us poor seismologists, this is all we've got. And trying to predict further into the future is almost impossible. So, but it does seem to look like we've had a pulse of activity in the 1960s, and now we're entering into another pulse in a global sense. So we must take a physics-type approach to looking at these earthquakes. So what is the cause of earthquakes? Well, this is a very simple model of what the Earth looks like, and you can think of it like a pot of soup. If you have a very thick soup bubbling away on the stove, turn off the stove, and eventually you'll form a little scum on the top. And if you let that cool off and disturb it, it will sink into the warmer soup below. And that's like a convection. And the reason why it sinks is because it's cooled off. The top scum has cooled, become heavier, and then decided to sink. The Earth is very much like that. It was once molten and convecting, but the very top, the top 130 kilometres, which includes the mantle and the crust, has cooled off and is now just a little bit more dense. This is density. It's about 1% heavier than the yellow material below. And if you can somehow break the surface tension of this the green material, it will sink, and you'll get sort of action. It will sink down into the lower mantle, and that is essentially plate tectonics, and that is the cause of just about all the earthquakes that we know. It is this process of redistribution of the cooled material at the top down into the lower mantle. And in New Zealand, we sit right on one of these plate boundaries, and this is happening beneath our surface, and this afternoon's earthquake was right down on about 200 kilometres deep on this Pacific slab as it goes under the North Island. So, if we then look at the earthquakes of the globe, you can see the Pacific Rim of Fire, and the earthquakes all around the Pacific, and these are the regions where that mantle is diving down into the Earth, the subduction zones. You also get earthquakes in the mid-oceanic ridges where the plates are being created, where the molten material is coming to the surface and being created. But most of the earthquakes are these subduction zones, and we happen to sit on them. We've got two of them going on in New Zealand. Okay, so here we come to New Zealand, and here I've just shown from the GeoNet website the coloured plots of earthquakes, deeper than 40 kilometres, and they're colour-coded from 40 kilometres, the orange ones, to the blue ones at 200 kilometres deep. And that's where today's earthquake was. It was right under this region here. You see my little cursor? And if you take a cross-section through Wellington, this is what it looks like. And this is plate tectonics. This is the subduction zone under Wellington, and you can see the earthquakes clustering around the plate boundary where there's a lot of stress and tension going on. They're scraping past one another, and then the much deeper earthquakes further down, which we don't really understand that well, like the one this afternoon. But certainly the ones here underneath the Wellington city, you can see this is a depth at about 24 kilometres. This is the Wairarapa fault and the Wellington fault, which all come off from that subduction zone. So let's now switch to today's earthquake, and this is what the information that I got from my graduate student. The first thing that occurs is that the USGS makes what's called a solution for it. It's much easier when you're sitting outside of New Zealand to gather all the seismographs from around the world, and you can focus then on the what's called the focal solution for the earthquake. It's like a beach ball, and really what it's showing is that if you had a ball right down on that earthquake, this is how it would deform, and the yellow means it's being pushed upwards, and it's what we call a thrust fault. It's been squeezed and pushed upwards along one of these planes. And on the far side is the shaking. You can see here the reports of shaking. And it's a very interesting pattern, because right above here in the King Country and the area where the earthquake was, the shaking wasn't that bad at all. But it's really over to the east and down to Wellington and also right down to Christchurch that it's very intense. And part of the reason is that the waves travel up that subduction zone that acts like a stress guide and transfers the energy very efficiently to these areas to the east and into and then right down into the Marlborough area. These are reports of shaking, and so the dark colours are the intense shaking, and to some extent these are biased by the large population centres. So the large population centres will have a much bigger range of perceived shaking, and so that's why I think you get the intensity in the centres like Wellington and Christchurch. It doesn't mean to say that it was actually stronger there. It's just a bias that comes in. So that was today's earthquake. It was a very unusual one in the sense that earthquakes on the subduction zone itself at those depths tend to be ones which are tensional, which pull apart, but this one looks like it's compressional. So there'll be a lot of interest in that. Okay, so let's just go to how we deal with hazards in New Zealand. This is a traditional way of doing it. We look at active faults, which are measured on the surface. These faults, you can see the purple ones and the red ones. The red ones are the very active ones in the last 2,000 years. The purple ones have surface rupture of greater than 2,000 years. And then we regard that as a means of mapping that into the hazards, so that the red colour here are the most forecasted as the most hazardous regions, and the blue and towards the purple gets progressively less. And this is a method that's been used in Japan and California and here as well. But if you look at this, you know what you know about recent earthquakes in New Zealand, you would say it hasn't been such a good predictor in the sense that Christchurch is regarded as rather low. It actually has about the same hazard as Whanganui, for example, and not much different from Auckland. And also Hawke's Bay doesn't have a particularly strong hazard, yet our most devastating earthquake in terms of loss of life was in Napier in 1931. So we need to look at this, and I think there's been a lot of work recently to try and unravel if this is a really good method of looking at hazards. Here I've let the same map plotted against all the crustal earthquakes. So these are the shallow earthquakes since 1930, and the blue dots are their magnitude 6 earthquakes. We have a new one to put on there today. And you can see once again, it's not our hazards map would not be a particularly good predictor of where we're going to have earthquakes. And if we look at the list of, this is a list of 18 earthquakes since 1843. And in terms of faults, only the red ones occurred on known faults. Out of 18, only 3 are on known faults. Most of our big earthquakes don't actually rupture the surface, like the Napier earthquake didn't rupture the surface. It caused a large uplift around Napier, but no fault trace came to the surface. And just about all the earthquakes, the major earthquakes that we have, are in that same category. The blue ones are where the rupture did come to the surface: Murchison, Inangahua and Darfield. And the other ones, they didn't. So by using faults as a means of suggesting where the next earthquake's going to be is not a particularly useful method. And the Kaikoura earthquake has now put a new sort of flavour on this as well, which I'll come to. In terms of what you notice, you might notice there that there's two earthquakes there listed for Whanganui, one in 1843 and one in 1897. Well, there's quite a lot of work being done on these historical earthquakes by people at GeoNet and elsewhere. And you can dig this out of the either the GeoNet website or from the Encyclopedia of New Zealand. And this is where they put now what was called the 1843 Napier earthquake. So it wasn't in Napier at all, it's well out to the east. But in 1843, most of the settlement, the European settlement, was very strong here in Whanganui, not out to the east. And so these reports are very much, in those times, very much dependent on written accounts. But the 1897 earthquake probably did occur here. So this comes from the Encyclopedia of New Zealand website, where there's a whole section on Whanganui earthquakes since 1840. And the interesting thing I think about this is all Macaulay scale, so these are reports of shaking, is that Whanganui does get a fair amount of shaking from distant earthquakes as well as local ones. And this is probably due to the local geology that you have here. You're built on a sedimentary basin, which is about 3 kilometres thick. And so that is not as rigid as, say, Wellington's Great Wave. So when an earthquake does come through here, you'll get a bigger amplitude of seismic wave coming through. So it's a foundation issue. But certainly the 1897 one seems to have been, by that time there's much more European settlement around, and that's probably was centred quite close to Whanganui. And it was a magnitude 7, which is significant. We have no idea of the depth. So what controls the level of shaking? Well, first of all, obviously magnitude of the earthquake is important. That's the more energy that's released, the distance from the earthquake, and then the local geology. And I think today's earthquake really demonstrates this thing of distance. Luckily it was 200 kilometres deep, so you got a fair amount of shaking, but the aftershocks will be very minimal because it's so deep. And this local geology, this is the problem probably that we have here in Whanganui, is the soft sediment which tends to amplify the shaking. So the one way we have to deal with that is through engineering. So what about the Kaikoura earthquake? Well, this was you obviously felt it here. I remember feeling it in Wellington. It was pretty scary. But this has given us a new insight into these earthquakes as well, because when this earthquake went off, it was right at the end of the subduction zone here. This is where the subduction zone ends, where the Pacific plate goes under the Australian plate, and then we have another subduction zone here where the polarity shifts around. But it's right at the very end, and it was what characterised the Kaikoura earthquake was, it wasn't just one fault that went off, it was a whole bunch of them, all went off at once. And this recent interpretation by one of my colleagues in Victoria shows that, in fact, what happens was that it was slip on this, what we call a mega thrust, or the subduction zone, that then triggered off all those earthquakes to bust off all at once. So really it's refocused our thinking about what is the role of faults in earthquakes. Are they the cause or are they the effect? Now this may sound a sort of semantic thing, but it's actually very important. And it looks more and more that it's the effect of something else, that it's this motion down here on this giant megathrust, which is the key source of most of our earthquakes. And the more we can understand about how stress builds up on this, the better we are in trying to understand how earthquakes occur in New Zealand and places like Japan as well. And so there's going to be a renewed focus, I think, now on using the GPS techniques to monitor the way that the stresses are building up on this major fault zone called the megathrust, which is essentially the boundary between the two major plates. And the faults themselves, well, they're just an effect of this slope. So if we look at these elsewhere in the world, at this megathrust, here's the Wellington one. There's Tohoku, the Tohoku earthquake under Japan. And if you look at the depth of, that was a magnitude 9 earthquake in 2011. Here it is here. It's at a depth of 24 kilometers, which is a very critical depth. And this is exactly the depth that the megathrust is beneath Wellington. And so this has been quite, it's making us a little bit nervous. And there's a lot of talk now about will we get the same sort of magnitude 9s in New Zealand? Well, it's a slightly different situation, and what we do know is that what earthquakes we have had since European settlement, like the 1855, was a magnitude 8. And it's been, this is it here, this fault coming to the surface here. So we hope that this is how this system works. It relieves the stress through magnitude 8s rather than these magnitude 9s. So having a magnitude 8 every 300 years is much better than a magnitude 9 every 1,000, because of every magnitude is a 30 times increase in energy coming from the system. So that's the situation in Wellington. What about Whanganui? Well, this is a cross-section now through Whanganui, just offshore here, A' with the earthquakes, and you can see there's two sets of earthquakes. There's earthquakes along the top, that's a depth, that line there is a depth of 15 kilometres, which is the mid-crust, and you can see there's a big cloud of earthquakes in the lower crust, and then these earthquakes are in the subduction zone. So if we put an interpretation on it, it's something like this. So the earthquake we had today was at 200 kilometres, one of these guys down here. And we don't really understand the mechanisms of how and why these earthquakes occur. And it's very unusual to have such large ones at that depth. And then there's the megathrust up here, which we know is a very dangerous one and can produce earthquakes. But these ones under Whanganui are quite interesting because they're lower crust and they create a sort of swarm-like activity. And some of you might remember back in about 1980, there was a lot of earthquake swarms here in Whanganui. I remember I just started at the geophysics division of DSIR, and one of my first jobs was to come up and monitor these earthquakes. As soon as we got here, it stopped. It was just, so, well, we thought we did our job. And, but it was quite, it was quite a concern. But this is typical of what happens when water gets, we think what's happening is that as the subducted plate comes down, it releases water through chemical reactions, and this permeates into the bottom of the crust here, and this then releases lots of little earthquakes, and that's what that swarm activity is. And they're never going to be really big ones, but there'll be lots of little ones. So they're not, I don't think they're going to be your trouble. It's going to be this event here, which will affect, of course, the rest of the country as well. But the small swarm events, although they're uncomfortable and a little bit scary, they are self-regulating. They won't get up to the big magnitudes. Okay, so that's earthquakes. Let's talk a little bit about volcanoes. And you know that just to the north of you, you have two volcanoes, Mount Ruapehu and Mount Taranaki. But what you might not realise is that there's a line to the north of each of those volcanoes suggesting that this whole sequence is migrating this way. And, yeah, but it's coming your way. But what we can do is, as geologists do, they can date the volcanoes and look at the rate at which they're migrating down here. So that's a very useful thing to do. So here's the volcanoes and their dates in millions of years. And there's actually two dominant types of volcanoes here in the central North Island. Three if you count, of course, the Auckland basalts. But let's just park those for a minute. These are the andesites. The black ones are the andesites, which are called low potassic andesite, and that's a sort of chemical term, and they are the ones that are coming off from the subduction zone. And you can see they have a regular type of rotation and migration down to here, quite slow through the Coromandel Peninsula, and from about here down, it's going reasonably quickly, about 30 millimetres a year. And here, these green ones are what's called the high potassic volcanism, slightly more disorganised through the Waikato and Mount Taranaki. And these are distinctly different from the ones to the east in terms of their chemistry and their origin. But you can see over the last 2 million years, there's been a very strong migration down that way. And you can see that both that's heading that way and that's heading that way. They're heading down here, all right. They're going to get here. But let's just look at the rates. So I've drawn this diagram. So those are the sort of rates. 25 million years, 33 millimetres a year. 25 millimetres a year, that's about 2.5 centimetres. That's about the rate that your fingernails grow. So if you do the calculation, in 3 million years they'll be here. So relax. So volcanism is not a big issue for Whanganui. Let's move on from the volcanoes. Okay, so the last topic I wanted to address was GPS and mean sea level change. And this has of course been in the news a lot lately. It's the major issue of our times. As you can see from that plot on the far side, this shows global change in global sea level. The rates from 1900 up to about 1930, it was about 0.6 millimetres a year, and then it's increased to 1.4 up to the 1980s, and then with the onset of satellites which can actually measure the height of the sea surface, we can now see in the last 30 odd years we're getting up to 3 millimetres a year. So what does this mean for us? Well, it depends where you are in New Zealand, because New Zealand is not like a rigid block which sits in the sea like a dish. So as the sea level rises, it just passively sits there. It's deforming. Some parts are going up and some parts are going down due to this plate tectonics things. And so it's very important to understand what your part of the country is doing. And it's particularly important to let the insurance companies know when they try and increase your insurance rates because you built the site close to the mean sea level. So what we have now in New Zealand is a series of GPS monitors which are run by GeoNet and shown by the blue dots. And you can see they're heavily weighted to the North Island because we had an issue there with slow earthquakes in over the last 20 years, and we've been trying to monitor them. And the South Island is hopelessly undersampled, which is a shame. But nevertheless, we can use these data from these sites to measure the relative change with respect to the centre of the Earth, not with respect to the sea level, but with respect to the centre of the Earth. That's what GPS does, because you're measuring from a satellite array which is rotating about the Earth, and the reference is the centre of the Earth. So let's see what that data is starting to look like. Well, these are permanent stations which sample every minute or so. And so if you take a station, this is New Plymouth, and what you see is there's a whole series of observations. The sampling rate there is more than a minute, but it's like every few minutes, and it's over a period of about 12 years. You know, it's more than 12 years or so. And you can see it's quite noisy, but you can start to see a trend developing. And what we find for most of the stations around New Zealand, once they've been in for about 6 years, we can start to see the trend, whether it's going up or down. And you can see New Plymouth is slowly going down. So don't buy real estate on the shore of New Plymouth. But the rate is about 1 millimetre a year. Yeah. So, and it could be due to a whole variety of reasons. So what we did, I worked with a colleague from Switzerland. We took the GPS data from all the GeoNet stations and made this map for the whole country for the period 2002 to 2015. And the colours represent the rates. So the blue is going down, it's negative, and the red is going up, it's positive. And you can see some very obvious things like the Southern Alps are going up, but the rest of the South Island, we can't really see a pattern very well because there's not enough data. But the North Island, we're starting to see a very consistent pattern. And down the eastern side of the North Island, it's steadily going down at about 3 millimetres a year. So if you add that to sea level change, that means the effective sea level change is 6 millimetres. So that's not a place to buy your batch on the seashore. But you guys are not a bad shape. We're going up here, very small amount, about 1 millimetre a year. So, which is certainly better than our cousins, Hawke's Bay cousins situation. And then in the middle of the North Island, the whole Rotorua-Taupo area has got the most massive subsidence area. And this is a volcanic process, but it's over a very broad region. It's not associated with a single geothermal field. It's over a very broad region, and it's ringed to the north along the Bay of Plenty coast by an upland. And these are individual stations, and you can see this red one here is the station on the Bay of Plenty coast, and these ones here are the stations at Rotorua in here. So, and you can see that from 2006 to 2012 they're going in opposite directions. So as one went up, one went down, it's sort of seesawing effect. And between the two, you'll get a very large tilt. So the coastal regions of the Bay of Plenty are slowly tilting backwards, and the rivers can't get to the coast. And this is where Edgecombe town got flooded. And if you look in those areas, you'll see that the rivers just are very meandering around, they're having a real difficulty getting to the coast. And we think this is part of the problem, this tilting that's going on in that area. So that's probably the most hazardous story to come out of this data set, apart from what we're seeing here along the east coast. And we can understand this from, because what happens here is, this is the subduction zone going here. And this little cartoon, and it will show you what's happened. So if you can imagine, this was Napier sitting here with a tropical island here, and we'll see if this will work for us. Yeah. So this is moving now, and you can see on the top is what the GPS signals will be showing, and we'll get to a point of 300 years, and then it will bang, there'll be an earthquake, it'll rebound and come up again. So I'll just run that through again, because this is a very good explanation of what we see effectively for the eastern North Island. And so the top plots are showing the heights for the different parts. So imagine this would be Napier going down over a period of 300 years, it'll be subsiding, then it'll suddenly come up. And of course, that is what happened with the Napier earthquake. If we go to the next slide here, this area where they built the airport was once a lagoon, and after the earthquake, it came up. And if they'd known then what we now know about this cycle, they might not have built it in that place, because now, of course, it's going down again. And can expect it to be pulled down for another 200 years until it reaches that sort of situation. So this is the sort of thing where science can help us not predict earthquakes, but really understand different areas of our own country and the world, and what is likely to happen in the future. So that's a very, the Napier earthquake is a very important earthquake for us in understanding how the cycle of earthquakes, in this case about a 300-year cycle, works. And we can expect Wellington will go through the same cycle as well. At present, we're in the phase where it's going down and it's stuck, but at some point it's got to bounce back with a major earthquake, and then we'll see everything uplifted again. As you can see in the geomorphology of the Wellington area, there's lots of raised terraces that come up. So what else do we have in this area? This is some work that was done by one of my colleagues on the raised terraces, and you really have wonderful geological examples around Whanganui, and I want to try and get across to you how you can look and interpret some of the structures in your own backyard and interpret them in terms of geology and active tectonics. And one of them are the raised terraces that you live on here. As you go out of the city to the north, you go up onto a terrace and you sit up high for a long time. And as you go south, you sit up high as well. And these raised terraces are showing that the uplift going on in Whanganui has been going on for a long time, like nearly 1 million years. So these are rates over 700,000 years, and those are rates of uplift measured geologically, and maximum is about 0.65. And so you're very familiar with these terraces, you probably take them for granted, but these are fantastic features, and it's much better to have them than not have them, because it means you're heading up and you're working against sea level rise. And the other things we can learn about in this area, of course, many of you have probably been down the Whanganui River, these fantastic gorges. Why are these gorges so steep? Because we know the erosion rates in New Zealand are so fast and so rapid that these would not last very long. And the reason, once again, is that it's been uplifted at a rate which is faster than which erosion can bevel them off. So we can play this game by making this a digital map of the area of the Whanganui River, and we can take that map and then make it what's called a surface just of the peaks, like a mathematical surface, and then subtract that again from the data to get to what's called the incision. And so this is the incision map, the measure of the depth of the valleys, if you like, and then we can contour it, like over there. And our argument is that over the last 500,000 years, this is where the maximum uplift is occurring. So we're getting uplift just to the inland, and it's progressively coming down towards the coast. Other features that you have in your landscape here are these the Papa mudstones, and of course as you go right up to Waiouru, the limestones up here above the Waiouru military camp, they've got this very distinctive slope to them. And then once you get to Mangahueka, if you look out the car window, that's just taken from the car window as I sped past, you can see the dip, the way that they're just dipping to the south towards Whanganui. And this represents a major structure right into the centre of Whanganui Basin, and these are the contours of the thickness of the basin. So it's one of the really major geological structures that we have in New Zealand, which is preserved, which runs effectively from Hamilton all the way down to Marlborough Sounds. And you can see it by just looking out the window here and observing it as you drive from Waiouru down to Whanganui. So, and as we go into offshore from the city, this is what the sedimentary strata look like here in the Whanganui Basin. This is work by Brooke Tozer, who's one of our students who comes from the city, and it shows this massive amount of sediment which is now accumulated beneath, just offshore from Whanganui. And as we go down to the Marlborough Sounds, you can see this whole area is coming down and it's progressively been uplifted to the north. So if we put all that together in a sort of diagram, it looks like this. Now I'll put the geology map on its side, and if you look from B dash to B, what's happening is these are the rocks, the sedimentary rocks of 15 million years to the very young ones at 1 million years. They've been laid down progressively to the south and then uplifted and then subsiding down to here. So it's a structure nearly 300 kilometres long, and and the pivot point is really where we are now, here at Whanganui, where this area is going up and will progressively go up more and more as that axis moves this way. So in a sense that is good news, because it will keep your head above the water for years to come. But of course, the rate of uplift at Whanganui is about 1 millimetre a year, and the sea level rise is 3. So effectively, your effective sea level rise is 2 millimetres a year. But that's much better than being in Hawke's Bay, where it's 6 millimetres a year. So I'm trying to be positive. Okay, and of course, last time I talked about the ground mountain ranges, a large mountain range now buried beneath here in this whole process. And you can see from this map of topography, the very distinctive topography of your area, of the raised terraces, and the very distinct topography of the drowned Marlborough Sounds. But it's all part of the same process, this gradual uplifting and tilting. It's sort of like a standing wave moving from north to south through the geology. Okay, so just finish off on a couple of unanswered questions. This was the Cook Strait aftershocks. This is when this earthquake actually occurred just as I was driving down to give a talk at Wanaka. It was exactly the same circumstances as this afternoon. It occurred at 2 o'clock in the afternoon, and I was driving to Wanaka. I didn't know, because there's no radio reception going through Central Otago, that this earthquake had occurred, and arrived down there. And we said, "What? Tell me about this earthquake that's occurred." I knew nothing about it. Today's situation is somewhat better, but I should stop going around giving talks about earthquakes. But the interesting thing here is from this Cook Strait earthquakes and from the Kaikoura earthquakes is that they seem to stop in Cook Strait. And this is either good news or bad news, and this is always the dilemma we have. But what we do know that's going on in Cook Strait now is that we're having many of these slow earthquakes where we get movement occurring over a period of months, which is equivalent to, say, a magnitude 7 earthquake. But instead of occurring in 2 or 3 seconds, it occurs over a month. And so you get this sort of, it looks in the GPS, it looks like this sort of jump like that. And so it doesn't, you create no seismic energy, they're quite safe. And the other thing to notice here is you see there was one in 2003, 2008 and 2013. And you might notice that there's 5 years apart. They're very periodic. And that is a character of these slow earthquakes that we see elsewhere in the world. And then another one occurred in the Manawatu in 2005. So maybe the stress on the subduction zone in the Wellington area is being released slowly, we hope, rather than in the big Kaikoura events. So that's one of the things that we're investigating. There's a lot of people working on this problem of trying to understand slow earthquakes. You might have heard people talk about them quite a lot in the media. Okay, so I'll just sort of end on some of the activities that we do. We take students into the field. This is a local one in the Parapara Road, installing seismographs. We're always, the GeoNet network of stations is fine. It's a very good network, but when we want detailed information, we go and put our own instruments in a very tight cluster to study focused areas. And we've had quite a lot of work on this Whanganui Taranaki area, which to me is one of the most interesting parts of New Zealand. One of the issues we always have, we found out very quickly, is that cattle will eat our seismographs, they'll eat cable and everything, so we've learned to be fencers. So we've become pretty good fencers. And the farmers have been great in teaching us how to do fencing, actually, and very grateful for them. And then in the South Island, we've been working on the Alpine Fault, where there aren't many large earthquakes at all. You might have noticed on my plot that very few earthquakes on the Alpine Fault, and there's lots of little guys, very small ones. And to get those, what we've had to do to understand them is drill. We'll get some money to drill these drill holes, which are about 50 metres deep, and then put the sensor down the bottom of the hole. And that way we can record earthquakes to magnitude 0, very, very small earthquakes. And so there's been a lot of work over the last 10 years on the Alpine Fault using boreholes for seismometers. So just to summarise then, let's just do a quick geological hazard checklist for Whanganui. Earthquakes, yes, they're still an issue for you, be ready for them, but I think the main problem is your soft soil and the shaking effects. But you're certainly in a much better position than, say, Hawke's Bay or Wellington, in a sense, of being further away from the big mega thrust. Volcanoes, rest easy, not going to be here for 3 million years, no problems. And sea level rise, well, it's a problem facing all of us, but it's not as bad as others in the country. So rest easy on that. So thanks very much.